Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. In Module 1, the Boolean logic, we talked about the propositions and the related operations. And we talked about 4 operations: conjunction, disjunction, implication, and negation. So with these operations, we can build a compound proposition or statement from smaller ones. And then we talked about how to use the truth tables to compute the value of the compound proposition or statement based on the values of the smaller ones that make up it. Okay, so we also discussed two proof techniques. One, we use the truth tables. We build a truth table and to prove something is right or wrong. Or we use another technique called proof by contradiction. So now today we will talk about an application of the Boolean logic. Module 2, Boolean Algebra and its application in digital electronics. Okay, so here's the learning objectives for Module 2. The first one, we're going to talk about the rule of precedence for Boolean operators. Now, the Boolean operators are basically the same as the Boolean operations we talked about in Module 1. The conjunction, disjunction, implication, and the negation. Now, so since we're going to talk about the application of this Boolean logicals, we're going to introduce some new symbols. Okay, and then we're going to talk about the Boolean identities, and then we're going to use these Boolean identities to simplify some of the algebraic expressions. Okay, and then we're going to talk about the computer transistors and the gates. So some kind of computer, electronic devices that we can use to perform these Boolean operations. We're going to talk about a gate representation, or we sometimes call the circuit of Boolean functions. So now let's talk about Boolean algebra. Now remember, in Module 1, we discussed the Boolean logic. Now in Boolean logic, we talk about propositions or statements. A proposition can take on only two values, true and false. So now the Boolean algebra is more general. Okay, Boolean algebra is an algebra for the manipulation of objects. Okay, not just propositions. The objects could be something else, like a switch. Now in that case, the values for switch could be on and off. Okay, and or some object which takes value like a black and white, or like in the electricity, you can take like signals. You can take the signals like a low or high. So now why we want to actually extend the concept of Boolean logic into Boolean algebra? Because computers are built as collections of switches that are either on or off. Now we want to use the computer to solve some problems which are more general than just like a proposition. So now Boolean algebra is a very natural way to represent these digital information. Now later on, we're gonna talk about the computer hardware. So you will know that computers are built from various different chips, or circuits. So each circuit basically contains a whole bunch of smaller components called transistors. These transistors put together can build a little bit more complicated logic components called gates. So we're going to talk about this, and then we're going to talk about how the computer works. And the computer actually can take the digital information like a 0 or 1. So now in reality, the components used to build the computer systems are called digital circuits, and digital circuits use the low and high voltages. So each signal can be sent either as a low or high voltages. In digital electronics, we typically use the binary numbers, two numbers. Instead of using on and off, low or high, we use the binary numbers, 0 and 1. So it is common to interpret the digital values 0 as false and the digital value 1 as truth, or vice versa. It doesn't matter. It's up to us. So now, we in this class, we're going to actually use the value 0 as false and the value 1 as truth. So now let's talk about three common Boolean operators: and, or, and not. These are basically the same as the operations we talked about in module 1. So and is corresponding to the conjunction, or is corresponding to disjunction, and not is corresponding to the negation. Now, and also we introduce three different symbols to represent these three operations. We use the tilde to represent not, and we use asterisk to represent and we use the plus to represent or. Remember, in module 1, we use different set of symbols. Remember these three symbols. One is the angle up. We use this to represent and angle down we represent or, and this represent not. Now these three symbols are widely used in the digital engineering. Now the following two are the truth tables. Now these truth tables are basically the same as the truth table we talked about in module 1. So the first table basically include both the truth table for and the truth table for or. The second table is the table for negation. Okay, remember the asterisk represent and, the plus represent or. So the value listed under here represent the truth table for and the value over here represent the truth table for or. And that's the negation. If x is 0, then the tilde x, which represent the negation of x, is 1, and vice versa. If x is 1, the tilde x is 0. So now with the three operations, one is the asterisk, represent and, one is the plus, represent or, and the tilde represent negation. So now we need to define the rule of precedence. Now in module 1, we introduced the four operations, but we did not really talk too much about the precedence, the rule of precedence. There is a rule of precedence for in the Boolean logic, but we did not emphasize this. But now let's talk about the rule of precedence. So which basically, once we talk about the rule of precedence in this Boolean algebra, I think it also applies to the Boolean logic, because Boolean logic is just a special case of Boolean algebra. So now the reason we want to talk about the rule of precedence is that sometimes logic operation is very confusing. Just like a arithmetic expression, for example, when we talk about the additions and the multiplications, now we need to figure out in certain case what is the order of the operation. Let's take a look at the example. If we say we want to actually perform the operation like a 2 plus 7 times 10 divided by 2. Now we know in arithmetic expression the rule of precedence is the highest actually priority operator is the parentheses. Okay, that's the highest. Now the next one, is the multiplication, division, and then we have the addition and subtraction. So in that particular case, in this example, so when we try to evaluate the value for this expression, we know that there's no actually parentheses. So that's why we just take a look at the next level. So we have definitely we have multiplication and a division. And then we have a plus, which is addition. So we know that the multiplication and the division has the higher, precedence. So that means in this expression, we need to evaluate 7 times 10 first, and then divide by 2. Now, typically, if you have two operations that are at the same level, like multiplication, division, the order is actually basically from the left to the right. So that means you evaluate the multiplication first, and then you evaluate the division in this case. Now, if the division is actually before multiplication, you first evaluate the division. And then once you've done this, then like a 7 times 10 is a 70 divided by 2. And then the next step is you do evaluate the division. So 2 plus 70 divided by 2, that's 35. So then we actually evaluate the addition, which is 37. That's important, because if we actually don't follow the rule, you may actually get a completely different result. For example, if you evaluate the plus first, the addition first, then we will get 2 plus 7, which is 9, then 9 times 10, that's 90, and then 90 divided by 2, that's 45, which is not the same actual result. Now, same thing with the Boolean expression. So we have to define the rule of precedence. Now, in Boolean algebra, the rule of the precedence is like this. The not operator has the highest priority, followed by the and operator, and then the or operator. So in this particular case, we have A plus B asterisk C. So that's or, that's and there's no not. There's no not operator. So that means we're going to evaluate the B and C first. And then we evaluate A or B and C. So we evaluate and get the result first. Okay, so this is actually the same as A plus B asterisk C. Okay. So this is basically what we do. Now, if you follow the other order, for example, if someone say, if I want to evaluate the OR operation first, and then the AND operation later, what should I do? Now, in that case, you can use the parentheses. Okay, so if you want to say, I want to operate the plus first, and then operate the asterisk, then you need to put the parentheses. So that way, even though based on the rule of precedence, the OR operation is lower than the AND operation, but because you have parentheses, so you need to evaluate the things in the parentheses first. Okay, so the result is going to be different. So here's the example, right? So if we actually take a value like A equals 1, B equals 0, C equals 0. Now if we evaluate the OR operation A or B first, and then evaluate the AND operation later, then you got the result 0. Now on the other hand, you evaluate B and C first, and then evaluate the OR operation, you got 1. Now if there's no parentheses, now this second one is the right order. Okay, because this AND operation has a higher precedency than the OR operation. Now here's a summary of the discussions in the previous slide. So then suppose we have a value A equals 1, B equals 0, and C equals 0, and then we try to evaluate the truth value of the Boolean operation. Okay. Now the answer should be based on the rule of precedence. You should evaluate the AND operation first. So B is 0, C is 0, so 0 and 0, that's 0. And then A is 1, so A, 1, or 0, that's 1. Okay. Now again, as I said, what if we really want to calculate A plus A or B first? Okay. And then we evaluate the AND later. Then we can use the parentheses. Okay. So we can say A plus B and with the parentheses. So then A or B, because A is 1, B is 0, so 1 or 0, that's 1, right? So now you got a 1, and 1 and 0, that's 0 for AND operation. Very straightforward, right? So now let's take a look at the example. So we have a Boolean expression, or we define this as a function. The expression says it's x or not y and z. So we define these as a Boolean function, f, x, y, z. Okay. So there are three variables, x, y, and z, and each variable going to take on only two values. X could be 0 or 1, y could be 0 or 1, z could be 0 or 1. Now, how can we construct a truth table for this Boolean function. Now, in order to construct the truth table, we need to build the tables which includes all the possible combination of x, y, z values. Okay, so now this is typically the way I build my tables. Okay, so the first case, we assume all the values are 0. X is 0, y is 0, and z is 0. And the second one, I put x, y, z, and the z is 1, and x is 0, y is 0. And then 0, 1, 0, 0, 1, 1, 1, 0, 0. Now, if you actually familiar with the binary numbers, now you probably remember that with the 3 binary digitals, then you can build the natural numbers from 0 all the way to 7. Okay, all 0 basically means 0. This 0, 0, 1 means 1. 0, 1, 0, that means 2. 0, 1, 1 is 3. That's 1, 0, 0, that's 4, 5, 6, and 7. 7 is 1, 1, 1. So in that way, we're not going to miss any actually one of the combinations of x and y, z, x, y, and z. Now, to build the truth table, so we need to, calculate the values of a smaller portion first, based on the rule of precedence. The rule of precedence says which operator we're going to actually evaluate first. Yes, that's right. The not operation is going to be evaluated first. And then the AND operation, and then the OR operation. So let's say the not y, what is this? We need to first look at the value of y, right? So if y is 0, not y is 1. Y is 0, not y is 1. So it's basically the opposite. So based on the value of y, we basically built the list for not y. So this is 0 because the y is 1, 0, 1, 1, 0, 0. It's just the opposite of this. And then the next operator we're going to actually work on is the AND. So it's tilde y and the z. So now we have a tilde y here, and the z is here. So then we perform the AND operation between tilde y and the z. So 1 and 0, based on the definition of the AND operator, that's 0. 1 and 1, 1. 0 and 0, 0. 0 and 1, that's 0, right? 1 and 0, that's 0. That's basically, from the definition of the AND operation. So you can go back and check the truth table for AND operator. 1, 1, that's 1. 0, 0, 0, 1. Okay. So the only cases that the value is 1 is that when both of these operands are 1. Now the last one, so we have tilde y asterisk z, then we perform the OR operation. So here we have x, and we also have this, which is here. So x 0, 0, 0 or 0, that's 0. 0 or 1, that's 1. That's based on the truth tables for all operation, right? 0, 0, 0, 0, 0, 0, and 1, 0, that's 1. Because the rest of these value for x is 1, so then it doesn't matter what's the other value. It's always 1. So that's basically choose table, and that's the value for each combination of x, y, and z. So we got these final values. So is that simple? So now here's your turn. So let's build the choose tables of the following Boolean functions. Now the first function, f of y, x and y, that function takes two parameters, x and y. And then the second function is f of a and b and c. So let's work on this. Okay, are you ready? So let's work together on the first Boolean function. So the first thing we want to do is to build a table, right? So we want to build a choose table, so we need to actually build a table. Now the table should contain the value of x and y. So let's do this. So we're going to try to calculate the value for all the possible combination of x and y. So again, I use my actually general rule that the first pair of values is 0 and 0. And the second one is x still 0, y is 1. And x is 1, y is 0. And both x and y are 0. Okay. So again, this is corresponding to 0. This is corresponding to 1. This is corresponding to 2 in the decimal, and this is corresponding to 3. Okay. So for two variables x and y, we find out there are 4 different combinations. Now to build this table, to calculate the f of x and y, so we first need to figure out, we just need to calculate each of the component. So the first one we need to calculate is, we need to calculate the tilde, right? The tilde has the high precedence. So tilde x, tilde y. Now based on tilde x, on the tilde y, we will build the x plus tilde y, tilde x plus y, that's the second one, and then the f of x, so that's the x plus tilde y, and tilde x plus y, so that's the f of x, y. So now the tilde x can be built based on the value of x. So if x is 0, tilde x is 1. X is 1 or 0, tilde x is 1. So it's 0, 0, 0, 1, 1. So you got 1, 1, 0, 0. Now here for y, based on the value of y, 0 becomes 1, 1 becomes 0, 0 becomes 1, 1 becomes 0, right? And then we build x plus tilde x. So x plus tilde y. So this is actually OR operation. So x or 0 or 1. So you got a 1. 0 or 0, that you got a 0. 1, 1, you got a 1. 1, 0, you got a 1. Okay. Now let's take a look at the other expression. Tilde x plus y. So you have a tilde x, which is 1, y, 0, 1, 0. But this is OR operation, so you got a 1. Tilde x, 1. Y is 1, so you got a 1. Tilde x is 0. Y is 0, so you got a 0. Tilde x is 0. Y is 1, so you got a 1. Okay, by the definition of the OR operation. So now the last one going to be the AND operation between these two, right? X plus tilde y tilde x plus y. So this 1, 1, you got a 1. That's the AND operation. 0, 1, you got a 0. 0, 1, 0, you got a 0. 1, 1, you got a 1. Okay, so that's the truth table for the first function. Okay, so let's quickly work on the second example. Okay, now, so first we want to build the table. So there are three variables, A, B, and C. So let's say A, B, and C. So now we have a value for A, value for B, and a value for C. Again, we need to actually include all the combinations of value of A and B and C. So that first one, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and a 1, 1, 1. Okay. So again, the first case we need to do is, so we need to calculate A and B, because that's something we need to have. And we also need to calculate the component B and C, right? B or C, I'm sorry. So here's another B or C. And then the next one we want to build is A and B or C. B times B plus C. And then the final. So we just actually add these three together. So you got the F of A, B, and C. So with the value A and B, you try to build A times B. So that's AND operation, remember. So 0, 0, you got a 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, that's 1, 1, 1, that's 1. Okay. And B plus C, that's all operation, right? So 0, 0, you got a 0, 1, 0, 1, you got a 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. Okay. Now let's take a look at the A and A times B plus C. So A and B or C. Okay. So here's A, B and B plus C. So that's 0, 0, 1, 0, because this is an AND operation. 0, 0, 0, 0, 1, 1, that's 1. 1, 1, that's 1. 1, that's 1. And B times B plus C. Again, B plus C, that's 0. B plus C, that's also 0. 1, 1, 1, 1, that's 1. 1, 1, that's 1. What's next? Okay, 0, 0, that's 0, 0, 1, 0, 1, 1, 1, and 1, 1, 1. Okay. Are these correct? Yes. Okay, so now we have the OR operation. So actually, you can first actually do the OR operation between this one and this expression, but you can do all of them together. So it's just 0, 0, 0, that's 0, 0, 0, 0, that's 0, 0, 0, 1, it's 1. As far as there's one expression is 1, then the result is 1. So 0, 0, 0, 1, that's 1, 0, 0, 0, that's 0, 0, 1, 0, 1, 1, 1. Okay, so it's a 0, 0, 1, 1, 0, 1, 1, 1. So that's the truth table. Okay. In this slide, we were introducing of the Boolean identities. Now, this identity can be used in Boolean algebra. Now, in general, in mathematics, an identity is a statement which is true for all possible values of its variable or variables. Now, for example, when we talk about algebraic identities, in algebraic identity, we have this x plus 0 equals x, which basically tells us that anything, which is x here, added to 0 equals the original anything, which is x, no matter what value that anything might be. So that's one of the algebraic identities. Now in Boolean identity, so they are very similar to algebraic identity, except the operation here, like asterisk, it's not multiplication, it's AND. And plus here is not addition, but it's OR operation. Now this identity can be widely used in the Boolean algebra. Now we can use this identity without even proving it, because it's always true for any variables. Now, so we can use any of this identity, okay, the Boolean identities. We know they are all truth. So we can pick one of these and prove it. For example, let's take a look at the first one under the AND form. So there are two actually symmetrical identity forms. One is AND form, the other one is OR form. Okay, they're symmetrical. So let's take a look at this first one. So the first one, identity law says 1 and x is always the same as x. Now we can prove this by using the truth table. So let's say on the left side, what's the truth table for the left side? Now there's a one variable, okay, which is x. So we can pick the value of x, okay. So suppose the value of x is 0, then what is 1 and x? So that's going to be 1 and 0, and this is going to give you the 0, right? Now if x is 1, then we have a 1 and a 1. This gives you 1. Okay, so that's the truth table for the left side. And the right side, so if I have x and the value is x, 0, 1, 0, 1, and then look at this column. So we got exactly the same values. So both the left side and right side have the same truth table. So that means this Boolean identity is always true. So we can actually always prove the others. So here I'm not going to spend much time to prove it, but you can use these identities without even proving it. Now these identities are very useful when we try to simplify the Boolean expression. Remember we mentioned that you may be able to create many different Boolean expressions, and these Boolean expression basically have the same truth table, and they are basically basically equivalent. So now how to prove this? One of the way you can prove is using the truth table. The other one is to use the Boolean identities. So we can derive from one expression and eventually we lead to the other expression. Okay, now we talked about the Boolean identities, and I said that we can use the Boolean identities to simplify some of the algebraic expression. Now let's take a look at the example, and we can actually get some idea what does that mean. What does simplification of algebraic expression mean? Let's take a look at the example. Remember, I'm not going to introduce a very complicated one, but I just use the one of the Boolean identities. So that's the absorption. Okay. So we remember that we can say x times x plus y is the same as x, right? So that means the expression on the left is identical to the expression on the right. Now, clearly, we find out, these two are identity, but so they basically generate the same value, okay? But you look at the left side and right side, you find out, wow, the right side is much, much simpler than the left side, right? So let's attribute a truth table to show this is the case. Now, for the truth table on the left side, we can actually, there are two values, x, y. So we have, all the possible combination of x and y. And then we try to figure out what's the value on this. Okay. So let's first build x plus y. And then we build x times x plus y. Okay. So x is 0, y 0, x or y, that's 0. 0, 1, that's 1, 1, 0, 1, 1, because that's all operation. And then let's actually do the AND operation between x and x plus y. So 0, 0, 0 and 0, that's 0, 0 and 1, that's 0, 1 and 1, that's 1, 1 and 1, that's 1, right? Now the right side, you'll be confused a little bit because right side there's no y. There's no y, okay? Now, but we can still actually put value x and y. Okay. So, but because there's no y, whatever value for y, it doesn't matter. It doesn't impact the final result for the expression, right? So when x is 0, y is 0, it's the same as x, so it's 0. Y doesn't matter. X is 0, y is 1, doesn't matter. It still follows the same value of x. X is 1, y 0 is 1. X is 1, y 0 is 1. So y doesn't play any role in these in the right expression. Now, look at the left side. Even though during the operation, it seems like you have to calculate the x plus y, the x or y. So you got 0, 1, 1, 1. But the final result is still the same as the value of x. You see, the value of x is 0, 0, 1, 1, and the final result for that expression has 0, 0, 1, 1. So the value of y doesn't matter. So that means, really, it's just a waste of time for you to do this because you actually work hard to evaluate x plus y, and then the final result has nothing to do with y, right? So that's why we try to figure out, well, looks like you may have many, many different algebraic expressions, okay? And many of these algebraic expressions are identical. But some of the expressions are much simpler than the others, right? So like this case, this is a simpler case. Now in this case, I would prefer to use this one. Forget about the one on the left, right? So that means if I can simplify, I want to simplify the expression. Not just for my for my own, cause, but also in reality, this is very important. Why? Because in the computer, you know, design, in the electronic circuit design, so you can design a logic component. The logic components can perform some kind of operation to do the logical operation. Now, these logical components are basically built based on the logic expression. So that means you can actually build the same, build a different logic circuits. Some of the logic circuits are more complicated than the other one. However, these two logic circuits basically perform the same operation. So if you build the logic circuits based on the left expression or build the logic circuits based on the right expression, then the right one is simpler. Okay? Now, which one you're going to choose? Of course, I choose the simpler one because it's going to do the same thing, but it's much simpler. And based on our common sense, it's going to be cheaper to build the logic circuits with a simpler logic expression, right? And also, hopefully, you're going to take consume less power for this because the left one is more complicated. So that's basically the idea why we want to simplify the algebraic expression. It's very important in the logic design. So now, before we move forward and talk about how to use the Boolean identities to simplify the logic expression or algebraic expression, now the first thing we need to actually talk about is how did we know that a Boolean expression is in its simplest form? And how to simplify the Boolean expression to its simplest form? Now, what's the definition? Now, unfortunately, there's no defined set of rules for using these identities to minimize the Boolean expression. It's simply something comes with experience. Okay. Now, so we will discuss this further after we introduce a new concept. It's called gates. The gate is a logic component that can perform some simple logical operation like AND operation, OR operation, or like a NOT operation. Now these gates are built based with all these smaller components called transistors. Okay. Now the first thing we know that there are an infinite number of Boolean expressions that are logically equivalent. Now we can have actually, in module 1, we actually talk about how can I prove that the two, Boolean expressions are basically the same. We use the proof techniques, right? Now, there are infinite number of them, Now, so that's why still to prove the equality of two Boolean expressions, you can create truth tables for each and compare these two truth tables. If the truth tables are identical, then the expressions are equal. So in that case, we prefer to pick the logic expression with the simpler form, okay, in this case. Okay, here's another example. let's try to prove two Boolean expressions. The first one is this. It's x plus y, which is x or y, and then tilde x plus y, and then you have AND operations to combine these two. And then we try to prove that this expression and another expression, just simply y, are equal. So again, this is a kind of situation that the left expression contains two variables, x and y. The right expression contains only y. Okay, so that means it really doesn't matter what's the value of y. It does not actually has anything to do with the result of this left expression, because the right expression says, it's just y, and because they're equal, right? Now, how to prove they're equal? That's another story. So you can actually prove this with a couple of different techniques. Now, one approach we can use is we can use the Boolean identity. Okay, we can use all these like idempotent law, unit law, distributive law to, simplify one side of the one side, and eventually we prove it's the same as the other side. Now the other one is using the choose table. We can use the choose table, or we can use another way to prove it, like using the proof by contradiction. So because we try to prove these two Boolean expressions are equal, so we can assume, what about if they're not equal? And we actually will lead to a contradiction. So that's another approach. Okay, so I call this proof 3, proof by contradiction. In any case, you can prove these two expressions are identical by using one of the proof techniques. So now we have talked about algebraic expression and also these Boolean operators. Now, how can we apply these in the digital electronics? Now, before we do this, let's actually introduce the computer transistors and the gates, some of the knowledges in the computer hardware. Okay, so a modern computer is made up of millions or even billions of transistors. So if you look at a small chip, now it looks very small, but there are billions of transistors built in this, silicon component. Now, these transistors work as each transistor work as a switch that has two states, on and off. Okay. So when a transistor is in an on-off state, it does not allow electricity to flow. When the transistors are in an on state, electricity can pass unpedally. Okay. So the transistor, you can interpret transistor as a light switch, and except that the switching of the transistor from on to the state off, or vice versa, is done electronically, not by your hand. Okay. Actually, a transistor is so small, how can you actually switch on and off by hand? Okay. So millions of these transistors are built on the wafer or silicon component to produce a device known as something called an integrated circuit. or sometimes we just call them chip. Now, so sometimes a chip is so small, they're in a cell phone, in your smartphone, in your laptop. Now these chip, they're small, but they are very powerful because they have billions of transistors built in there. Now, these transistors are actually logically put together, to create a big component. And all these big components are put together to create even bigger components, electronic components. And they can actually do these logical operations. So the diagram on the right basically, illustrate what a transistor look like. Okay, this is just logic diagram. So each transistor has 3 lines. Okay, a control or baseline. This is a control baseline, and an output line and an input line. So you can basically set a voltage, so on the control line. So then we can switch the transistor into on state. So that means, so the electricity can, flow. It can pass through. Okay. Otherwise, we can switch the transistor into off state by not applying voltage on the control line. Okay. Now, so when we actually apply the voltage on the control line, we can actually use the number 1 to say, we set a voltage. Now, 0 basically means we don't apply a voltage on the control line. So if you actually set a, the value is 1, then the electricity can pass through. Now, if it's 0, now this is actually disconnected, So this is just logical diagram, It's not like a light switch, so you can manually switch on off, but it's controlled by the electricity, controlled by the voltage. So now if we actually view a computer as a brain, then the transistors made up of the computer would be the cells, just like a human body. Then, a computer is a human body, and then transistor is just a cells. Now transistors can, control whether we can let the electricity pass through or not. However, because transistor is too small a component, so it cannot do any meaningful things. So then we just use the transistor to build a big component. Okay, just like a cell. So the cell itself is too small. So then we need to actually build as human organs from the cells. Now a transistor is too small an element that may not perform any meaningful things, just like a cell. Okay, so now the real significance of the transistors is that we can easily, put few of the transistors together to build an electronic device. And we call these electronic devices logic gates, or sometimes we just simply call a gate. So a gate produces the output of Boolean operations defined by the truth tables for AND, OR, and NOT. Okay, so these AND, OR, and NOT operations can be simulated using the gates. Okay, now besides the AND, OR, and NOT, there are some other gates that can perform some kind of different Boolean operations. Okay, so we're also going to introduce these, other gates. One of these other gates is called exclusive OR. Okay, a NOR gate, NOR instead of OR. Okay, and the NAND gates, NAND gate. So versus AND gate. So we have a AND gate, OR gate, NOT gate, exclusive OR gate, NOR gate, and the NAND gate. Okay, so we can actually introduce these 6 different type of gates. And we're also going to discuss how to build these gates from the transistors. In this slide, we're going to introduce symbolic representations for all these 6 gates. Now, first one is the NOT gate. If you look at this table, the NOT gate, we use the triangle and put a small circle at the very end to represent it. Okay. Now the NOT gate has one input line and one output line. Now input line we use A to represent input line, the X to represent output line. So then we can build a truth table for the NOT gate. Now if we apply voltage on the input line, that means the value for the input is 1, then the output is going to be 0. Now if we don't apply voltage on the input line, the output line will have the power. So that's 1. So this is the truth table for the NOT gate. And then here's the AND gate. We use this notation. Now AND gate has 2 input lines, A and B, and there's 1 output line, X. So we also use the electricity. If we apply electricity on one line, then that represents the value 1. If we don't apply electricity, then that means it's 0. So now with the combination of the values of A and B, then we can build the truth table for the AND gate. Okay. Now, for example, we apply electricity on both line A and the line B, then the output X will be 1. That means the output also has electricity, And here's a NAND gate. The NAND gate is basically the opposite of AND gate. So it's just the same AND gate, and then we put the NOT operation before it. The same with the NOR gate. The NOR gate is, you put the NOT gate, you will put a NOT operation before the OR gate. Now, exclusive OR is kind of, strange. It is actually tilde A times B plus A times tilde B. So now the OR table, the truth table for OR gate, the truth table for AND gate and the NOT gate are exactly the same as the truth table we just talked about before. Now the NAND gate is opposite of AND gate. NOR gate is the opposite of OR gate. So it's also easy to understand. Now the exclusive OR gate is kind of strange, because if you look at the table, now the output line is based on these 2 input lines. Now if both input lines have the same value, the output line is 0. And the input line has, if the input lines have different values, then output is 1. Okay, so that's the exclusive OR gate. To make the logical design a little bit easier, we're also going to introduce 4 more gates. Now, these gates are 3 input gates. So the first one is the AND gate, but it contains 3 inputs. Okay, And the second one is the OR gate, also contains 3 inputs. And also we have 3 input NAND gate and a 3 input NOR gate. So these are the 4 gates with 3 inputs. So that's a 3 inputs AND gate. And then 3 input OR gate. So this is actually the 3 input NAND gate and the 3 input NOR gate. Okay. So the table, you can, it's built here. You basically, just do the calculation for the input A, B, and C, then you generate the output. Okay. Now, for 3 input OR gate, now, so the truth table should be also very straightforward, right? It's A plus B plus C. So as far as one of the input is 1, then the output is 1. Okay. So the only case that the output is 0 is the first case, when all the inputs are 0. So the rest of the case, it will generate 1. Okay. So now the 3 input NAND gate is basically the opposite of the AND gate. So now since it's all 0 here and the last one is 1, then it's the opposite. And also the NOR gate, 3 input NOR gate, is the opposite of 3 input OR gate. So you got a 1 here, and then you got a 0 for the rest. So now let's talk about how to build these gates. Now the first thing we want to talk about is how to build NOT gate, because that's the easiest gate. There's only 1 input and 1 output. Remember, for the transistor, we said that the control line is the one that controls the on and off of the transistor. Okay, so if the control line is 1, that means we apply the power on the control line, then these 2 lines will be connected. So the power, the electricity gonna pass through. Now, if the control line is set to 0, then it's disconnected, like the current case. Okay. So now to build the NOT gate, we're gonna view the control line as the input of the NOT gate. Okay. So the control line now becomes the input. Okay. Now the source of the line that apply the power, that's a source of line. We actually use this as output. Here's the input, here's the output. And the other line, the emitter line, that's a collector line, that's emitter line. We actually set the emitter line to the ground. So that means ground basically means we touch the ground, so all the power are going to be, reduced to 0. So now let's see how it works. So suppose we actually set the power on the control line, so that means the value is 1. If the value is 1, that means the transistor the switch gonna be connected. So that means the collector line and the emitter line will be connected. So the power gonna actually pass through. Now when we apply the power, however, so that means normally the power source gonna be the value 1. But because we apply the 1 in the control line, so then emitter and the collector and the emitter are connected. So this directly connected the power line to the ground. So this will actually basically set the output line to 0 because the output line now is grounded. Okay, so it's pretty simple. Now, what about the opposite? If the control line is set to 0, okay, so that means it will be disconnected. Okay, so this the transistor, the collector and emitter will be disconnected. If it is disconnected, so that means the collector side will have the value 1 because it's connected to the power source and it's not grounded. So this is going to be 1. So if the control line is 0, then the output is going to be 1. If the control line is 1, the output is going to be 0. So this way, we actually build the NOT gate using one transistor. So now let's take a look at how to build a NAND gate and an AND gate. So we first talk about how to build a NAND gate because it's easier. Now, to build a NAND gate, we need 2 transistors. We need 2 transistors. Okay, so take a look at this diagram, the diagram on the left. So we have transistor 1, which has a control line 1, and we call this control line A. And then the bottom transistor has a control line 2, we call it B. Now the control lines of the transistors become the inputs. Okay, now the collector side of the transistor 1 connect to the power source, and also the collector side is also defined as the output for the NAND gate. Now remember, for a transistor, if we set the control line to 1, that means we set the value of the control line to 1, that means we're going to connect the collector and the emitter. So that says that we actually set the switch of the transistor to on position. Okay. Now, if we set the control line to 0, then the switch of the transistor is in off position. Okay. So now the second transistor, the transistor 2, is connected to the ground on the emitter side. Okay, so now let's see how it works. So if we set both the input line A and the input line B to 1. Now in that case, both transistors are switched to on position, so that means they're connected, right? So that means the power line will be directly connected to the ground, so any electricity will be drained to the ground. So that means it will be 0. The output can be 0. Okay. Now, in any other cases, either both the control lines set to 0 or 1 is 0, the other one is 1. So in either case, at least one of the transistors is switched off. So that means the power source will not be connected to the ground. So in all these 3 cases, the output can be 1 because they're directly connected to the power source, but not connected to the ground. So that's the truth table for these device. And this is exactly the truth table for the NAND gate. So that's why we actually build a NAND gate using 2 transistors. Now, the next thing we're going to talk about is how to build the AND gate. The AND gate is relatively easy because AND gate is the opposite of NAND gate. So all we need to do is we need to put a NOT gate on the output side. So this will actually generate the opposite output values for the AND gate than the NAND gate. So that says to build an AND gate, we need 3 transistors. Okay, so the additional transistors is used to build the NOT gate. Remember, we just talked about how to build a NOT gate using 1 transistor. Now, to build a NOR gate or OR gate, we also need 2 transistors. But instead of you connect these transistors seriously, we're going to actually connect these transistors parallelly. Okay, so let's take a look at the diagram here. Okay, so 2 transistors, they actually use parallel connection. Okay, so the transistor 1 has a control line 1, and we call it A. The transistor 2 use control line 2, we call it B. Now the collector side of both transistors are connect to the power source, and also it serves as the output. Now the emitter side of both transistors are grounded. Now you can see in this case how this is supposed to work. Remember, if we set the control line to 1, for example, we set the control 1 to value 1, then this can actually set the transistor 1 to switch on, right? So this makes the transistor 1 to switch on. So then it will connect the collector side and the emitter side. So that means if one of the control line is set to 1, then the output, both the output and the power source, will be connected to the ground. So the electricity will be drained to the ground, so the output will be 0. So that means here's what happens. So A, B. If the value of A is 1, then the output is going to be 0 because it's ground. Now, it really doesn't matter what is the value, the control line value of B. So if it's 1 or if it's 0, it doesn't matter because it's connected to ground anyway. So that means if B is 1, the output is 0. If B is 0, the output is also 0, right? Or if we set the control line B to 1, and even A is 0, the result is 0. The only case that the output becomes 1 is that both control 1 and the control 2 are 0. So in that case, both transistors are switched off into the off state. So that means the output is not connected to the ground. So that's basically the truth table of the NOR gate. And again, so the NOR gate and the OR gate are very closely related. So if we put a NOT gate on the outside, at the outside line, so then we can build an OR gate, because the OR gate is basically opposite of NOR gate. So again, so we can build the NOR gate with 2 transistors, and build the OR gate with 3 transistors. One transistor is actually served as the the NOT gate. So far we have talked about how to build a NOT gate, NAND gate, AND gate, NOR gate, and OR gates. So L gate. Now, in this slide, we're going to actually briefly talk about how to build a 3 import gates, from 2 import gates. So it's pretty simple. If you look at this diagram, on the left side is the 3 import gates, and the right side are two import, gates. So if we want to build a 3 import AND gate, then we can use 2 import AND gates. Actually, two import AND gates. So we can connect the AND gate to import AND gate that way. So you have a 2 import A and B, and there's output, and the output of the one AND gate can be served as input for the second AND gate. So this is how we're going to build the 3 import gates. Now it's very similar to build the 3 import OR gate. So far we have talked about 2 different topics. One, we talk about how to build a Boolean expressions, and how to build a Boolean expression using the Boolean operators AND, OR, and NOT. Now, and also we talk about how to, create a circuit, how to create using, these transistors, and then use the transistors to build the gates, and then we perform these, operations, to simulate the Boolean expression. Now, from one side, every Boolean function can be expressed by an algebraic expression in terms of a truth table. So a function may be expressed through several algebraic expressions on account of them being logically equivalent, but there's only one unique truth table for every function. Now, on the other side, a Boolean function can be transformed from an algebraic expression into a circuit diagram. The circuit diagram, basically, we're going to draw this using, various different symbols for the gates. Okay, we call it combinational circuit. Yeah. So these circuit diagrams are composed of logical gates connected in a particular structure, or vice versa. So basically, we build a relationship between the Boolean expression and the circuit diagram. Okay, so this gave us provide a way for us to design a circuit by first, define the algebraic expression. Okay, let's see how we gonna do this. Okay, so in circuit design, you need to do 2 types of operations. One, if you're given a Boolean expression, how can you convert this Boolean expression into the circuit diagram? That's one thing. So you convert from Boolean expression to the circuit diagram. Now, another operation is the opposite. So if you're given a circuit diagram, how can you find out what is the Boolean expression that is represented by this circuit diagram? Now here's the example. Now we need to find out what is the Boolean expression that is represented by the circuit diagram here. Now this circuit diagram contains 2 NOT gates, 2 AND gates, 2 AND gates, and 1 OR gate. Okay, so there are 2 NOT gates, 2 AND gates, and one OR gate. Now what's the Boolean expression? Now to do this, we need to start from the imports. There are two imports, A and B. Now each import is going to actually lead to one of the gates. Now we start from the simpler one. So let's say, suppose we have A, that's the import A. Now one A is split into two, and the one actually goes to the AND gate, the other one goes to the NOT gate. So now let's see, suppose the value is A. Now the NOT gate is going to basically change the value of A to opposite of A, right? If A is 1, then it will change, it will convert into 0. If it's 0, it convert to the 1. So if the import is A, so the output should be the tilde A, right? It's a negation of A. So same thing with for the import B. So then this output of the NOT gate should be tilde B. Now with this, now you can figure out the output for the first AND gate, because one import for the AND gate is tilde A, the other import for the AND gate is tilde B. So we have A and tilde B. Now here, for the other AND gate, one import is tilde A, the other import is B. So it's actually connected. So it's basically the same value. So then with the AND gate, you're going to generate tilde A times B. So now we have two Boolean expressions. These two Boolean expressions serves as the input for the OR gate. So the output for this should be A times tilde B plus, that's all, right? The tilde A times B. Now this is the Boolean expression represented by this circuit diagram. So this is what we have. So the Boolean expression that is represented by this diagram is this. That's it. Now it doesn't matter we have a parenthesis or not, because based on the rule of precedence, you always actually evaluate the AND gate first. Then you evaluate the OR gate, right? So with or without parenthesis doesn't make any difference. Okay, so let's wrap up the module 2 with these particular problem. So here we have a circuit diagram with three inputs, A, B, and C. The output is Q. So now please actually work on this diagram and try to figure out what's the Boolean expression. So I will actually post another thread on the discussion, so then you can actually work on this problem and post your answer. So you can actually, it doesn't matter whether it's right or wrong, but so we can actually share the answers, so we can see each other who, what is the result for these. So that's pretty much it for the module 2. Thank you.